All right, welcome to Basics to Brilliancy B2B. This is season 2 of trigonometry, unpacking all of the trigonometric questions within grade 12. This is episode 2, whereby we unpack all of those questions, whereby you are given some pieces of information and then you are required to sketch a diagram and therefore answer following questions based on that specific diagram. In episode 2, previously we unpacked the principles, basics, and the concepts just to ensure that the foundation is firm within trigonometry, and that understanding of those principles, basics, and concepts should serve you really well, specifically for this episode and the episodes to come. So I'd encourage that before this episode, you perhaps visit episode 1 and then you come back for this episodes and other episodes within this specific season 2. All right, without wasting any time, let us get into it. The first question focuses on being given two pieces of information. In this case, the first piece of information is sine beta equal to 1 over 3. And then the second piece of information is beta begins from 90 degrees to 270 degrees. So within this question, we must use these two pieces of information. Among these four quadrants, identify a quadrant that we will use, and then in that quadrant, sketch a right-angled triangle, and then label it, and then answer the following questions. The first question, the first piece of information that we are given is that beta, sine beta is equal to 1 over 3. Focusing on the constant itself, which is 1 over 3, we can see that it is positive. That means that the trigonometric ratio that we have, which is sine in this case, is also positive, right? And in the previous episode, we saw that actually sine is positive in the first quadrant and also in the second quadrant. So we can now go on and in the first quadrant make a tick, in the second quadrant make a tick as well. This is just to identify that so far we have those two options, first quadrant and second quadrant. And then we take the second piece of information, which is beta ranges from 90 degrees and all the way to 270 degrees. So where is 90 degrees and also where is 270 degrees? Then starting from 90 degrees, going all the way to 270 degrees. We get to see that, we have covered the second and the third quadrants. So this basically points us to the second and the third quadrant, the second piece of information. And then our goal is to then, among all of the identified quadrants, identify a common quadrant. And we can see that there is the identified second quadrant in the first piece of information, and there is the identified second quadrant also in the second piece of information. That means, therefore, our right-angled triangle must be drawn in the second quadrant. Then we can go and sketch our right-angled triangle in the second quadrant. We begin by drawing our hypotenuse and then we draw and complete the right-angled triangle with a vertical perpendicular line. And then we add our angle, which is beta in this case, and we always begin from the positive x-axis all the way to our hypotenuse. Now that we have our right-angled triangle, we must then label the sides of that right-angled triangle. For labeling of the sides, we go back to our first piece of information. We see that, okay. So we have sine beta equal to 1 over 3. And previously in episode 1, we saw that the definition for sine is actually opposite over hypotenuse. And that means the opposite side, which is the vertical side in this case, is 1 unit. And then the hypotenuse, which is the side opposite to 90 degrees, is 3 units. And then obviously we have a missing side, which is the value of x. And previously in episode 1, we learned about a very lovely theorem, which is Pythagoras theorem, that we can use in a right-angled triangle to calculate the length of one side if we are given the lengths of other two sides. In this case, we don't know x, so we are going to substitute in the place of x by x. We know y is 1, and we know r to be 3. And then we have x squared, 1 to the power 2, that remains as 1, 3 to the power 2, that becomes 9. And then we take our positive 1 to the right-hand side of the equation, it becomes minus 1. So we have 9 minus 1, which is 8. We're not solving for x squared, we are solving for x. So we must then take the square root on both sides of the equation. And then when you press your calculator, you will get x, 2x is equal to 2 root 2. That is the value from your calculator. But previously in episode 1, we learned that x can be positive or negative depending on the quadrant that has been used to sketch the right-angled triangle. In this case, that is the second quadrant, and within the second quadrant, the value of x must be negative. Therefore, the final answer or the value, the correct value of x is negative 2 root 2. Why? Because our diagram is on the negative side of the x-axis. All right, so in summary, now we have identified the quadrant, and then we have sketched our right-angled triangle, and then what remains is to answer those questions. And that is what we are going to do right about now. 5.1.1 cos beta. Previously in episode 1, we learned that cos is defined as the adjacent side, which is in this case negative 2 root 2. Negative 2 root 2, the adjacent side, over the hypotenuse, which is in this case 3. And that, folks, is the answer for 5.1.1. Moving along, we have now sine 2 beta, and then we see that we no longer have just beta now, we have 2 beta, and that streams to be a double angle for sine. And previously in episode 1, we discovered that the expression for the double angle of sine is 2 sine beta cos beta. Then we write the 2, we open brackets, and then we will substitute there the value of sine beta as per the diagram. We open another set of brackets, and then we will substitute there the value of cos beta as per the diagram. All right. Sine beta is opposite over hypotenuse, which is 1 over 3. Cos beta is adjacent over hypotenuse, which is negative 2 root 2 over 3. You press that in your calculator or you calculate using your head. You say 2 times 1 times negative 2 root 4, that root 2, that gives us negative 4 root 2 all over 3 times 3, that is 9. And that, folks, is the final answer for 5.1.2. Right. And then moving along into 5.1.3, we see that now we have cos of 450 degrees minus beta. And we realize that actually we don't have a reduction formula that contains 450 degrees minus beta as per the cast diagram that we learned in the previous episode. The problem here is 450 degrees. What is the problem with that? It is bigger than 360 degrees. So how do we then deal with angles bigger than 360 degrees? We have a remedy for that, as we have learned in the previous episode. We subtract 360 degrees from that angle greater than 360 until we get a value less than 360. In this case, we're going to get 90 degrees. So that means now we will have cos of, in the place of 450 degrees, we substitute 90 degrees, and then we say minus beta. And that, folks, is a normal reduction formula. We will ask ourselves which quadrant is represented by 90 degrees minus beta. And that is the first quadrant. What is the sign of cos in the first quadrant? That is positive. Since we have cos and we have 90, that means we must change cos into sine. Right. And we can easily get the value of sine beta from the diagram. Opposite, which is 1 over hypotenuse, which is 3, 1 over 3. And that, folks, is how it goes. Now, I have a challenge for you. We are given 2 pieces of information once more, that being the first, and then we are given the second piece of information, that being the second, and then using those 2, pick a quadrant, sketch a diagram, label your diagram, and then answer this question, which is sine of A plus 30 degrees. And that, folks, is an expression of a compound angle of sine. All right, I will show the solutions just now. So take a moment. I would encourage that you pause the video and then you attempt this question, and then you see the question, the solutions later. And those are the solutions, folks. As I have mentioned previously, in the previous slide, that here we have a compound angle of sine. And if you are confused as to where does that same come from, the S, blah, 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 That means, simple means you didn't watch episode 1. So I would highly recommend that you catch up on episode 1 and then you see such a lovely story of where does SCCS pattern come from and what does it even mean. All right. So let us categorize what we have been learning so far. We've been attempting the questions whereby we're given two pieces of information, that being the first and that being the second. And then what do we get from those two pieces of information? A diagram. And then from the diagram, we answer questions. So that is what we have unpacked so far. From this point onwards, we will unpack questions whereby we are already given a diagram, but it is not fully sketched. And then our responsibility will be to complete that diagram and then answer the questions. And that is the question that we will use to demonstrate such a problem. Here we are given O as the origin, and then we are given S as that coordinate, whereby X is 4 and Y is Q. And then we are told that the distance from O to S, which is called OS, is 3 root 2. So our responsibility now is to complete this diagram and then answer these questions. It's very simple to complete this diagram. You just draw a vertical line, which will be perpendicular to the x-axis. And then from there, we use the coordinate S to label the sides. X is equal to -4. So the x-axis will take that -4. Y is equal to Q. Therefore, the y-axis will take Q. And then we see that, so OS is that hypotenuse, which is our R. And then obviously this diagram is not fully complete yet because we don't know the value of Q. We must then calculate that value of Q. And when we calculate the value of Q, we are basically answering 5.1.1 already. So 5.1.1, calculating the value of Q. We will use a very lovely theorem, which is Pythagoras theorem. X squared plus y squared is equal to r squared. X is -4, so we substitute. Very important to note. The -4 must be within brackets, so that negative does not confuse you. And then the square outside brackets. For y is 2, and then r is 3 root 2, and then square. -4 all to the power 2, that will be 16. Q squared is Q squared. 3 root 2 all squared, that will be 18. And then we take the positive 16 from the left-hand side to the right-hand side of the equation, and then we get -16. 18 minus 16, that gives us a 2. And then we take a square root on both sides of the equation. We then get, from your calculator, a square root of 2. But remember what Q is. Q is the value of Y. And previously in episode 1, we studied that Y can either be positive or negative. Based on the diagram that we have currently, we see that, so it is below the x-axis. Therefore, our Q must be negative root of 2. All right. So that is how we calculate, folks, the value of Q. And then moving right along into 5.1.2, which is sine of theta plus 45 degrees. So this question is very similar to the previous one where we were working with sine A plus theta. So just in case you didn't get that, this is an opportunity to then even master it for the second time. So this is basically a compound angle of sine. And what is the pattern for the compound angle of sine? It is sine theta cos 45 degrees cos theta sine, yes, sine 45 degrees. What is that pattern? The pattern is S, C, C, S. Sine, cos, cos, sine. And then what happens to the sign between these two terms? We say that the capital letter S in sine stands for what? Stands for same. And what must be the same? The sign in the middle must be the same as the sign in the middle here. So therefore, since we have a positive between theta and 45 degrees, we are going to also have a positive between those two terms. All right. The sign remains the same. You can take that capital letter S from sine as sine stays the same. All right, let's move along. Now we will open a pair of brackets. What are we going to substitute there? The value for sine theta. Then we open another pair of brackets. What are we going to substitute there? The value for cos 45 degrees. And then plus, we open another pair of brackets. What are we going to substitute there? The value of cos theta. And then we open the last pair of brackets. What are we going to substitute there? There's the value for sine 45 degrees. So looking in the diagram, what is the value for sine theta? Opposite, which is negative root 2 over hypotenuse, which is 3 root 2. What? And then cosine of 45 degrees. Previously, in episode 1, we saw that cosine 45 degrees can either be 1 over root 2 or root 2 over 2. It's up to you which one do you choose. So we'll take 1 over root 2. And then cos 45 degrees is the adjacent side, which is negative 4 over the hypotenuse, which is 3 root 2. Sine 45 degrees, similar to cos 45 degrees, it is either 1 over root 2 or root 2 over 2. That is one and the same thing. So we'll substitute 1 over root 2. Right. And then when you multiply the two numerators, you're going to get negative root 2. And then you multiply the two denominators, you're supposed to get a 6. And then it will no longer be plus now. It will be this negative from 4 multiplied by that plus, and then we get a negative. So 4 times 1, that becomes 4, and then multiply the denominators, you're supposed to get a 6. And from there, you will get yourself negative root 2 minus 4 all over 6. If you want to, you can even take out the negative as a common factor, and then you get yourself that. Or you can, when you're at this stage, press a calculator. Then see what do you get. Perhaps you should get the same thing. But I would encourage doing the steps so that you know where does your answer come from. All right, let us then go to the last question, 5.1.3. 5.1.3, here we have cos of 2 beta minus 360 degrees. Previously, we learned on how to deal with a negative angle in episode 1. We said we add 360 degrees. So if we have there a numerical angle that is negative, in this case, which is negative 360, we must then add 360 so that it becomes positive. Then we get 0 degrees, and we are happy with 0 degrees. We will then substitute and say cos 2 theta plus 0 degrees, which is unnecessary. There is no need to write 0 degrees because it's going to disappear. So this will eventually come from being cos 2 theta minus 360 degrees to being cos 2 theta. And that, folks, is a double angle of cos. And then we can solve that using any of the expressions of cos, for example, 1 minus 2 sine squared theta. All right. And then we will say that is equal to 1 minus 2, open up a pair of brackets, and then within those brackets, we will substitute for ourselves the value of sine theta, which is opposite, that is negative root 2 over the hypotenuse, which is 3 root 2. And if you are the guy that prefers to use a calculator, you can then say 7 over 9. If you prefer to do it mentally, you are more than welcome to do so. All right. And that, folks, is the type of question whereby we are given a diagram and then we have to complete it, use Pythagoras to calculate the missing side, and then answer the required questions. Now, as you may expect, I have a challenge for you. Take that one as a question that you will attempt, pause the video, and then answer so that you can compare your answers to the solutions that are to come. 5.1.3 is very similar to 5.1.2 in this question, which we solved in this way. Also similar to this question. So it's a compound angle, but now it's a compound angle of cos, and we learned about that compound angle in episode 1. All right. So here are the solutions for that problem. As I've mentioned, 5.1.3 deals with the compound angle of cos. And where does the change come from? And where does the C come from? Where does the CCSS come from? All of that was unpacked in the previous episode. Right. Back to categorizing what we have learned so far. We have learned about a group of questions. The first one being given 2 pieces of information, you sketch a diagram, and then you answer following questions. The second group of questions is that we are given already the diagram. We must just complete it and then answer the given questions. Now we are going to the third set of questioning within the same category of questions. And this third set of questioning is a scenario whereby we are given now just one piece of information, not two, not a diagram, just one piece of information. We must draw also a diagram here and then answer the following questions. We must draw a diagram and then answer the following questions. So previously we chose the quadrant that we were going to use among the four quadrants of a Cartesian plane. Could have been the first, the second, the third, or the fourth. But in this case, we don't have to draw a Cartesian plane because we don't even have to think about which quadrant are we going to use. It is always the first quadrant. Why? Because the angle that is given here is 26 degrees, and that is theta. Why that angle is theta? Because that angle is between 0 degrees and 90 degrees. Remember what we said, or we said that in the previous episode, in episode 1, that every angle that is referred to as theta from that point, from episode 1, is an angle that belongs in the first quadrant within that cast diagram, belongs in the first quadrant. So an angle 26, which is between 0 and 90 degrees, belongs in the first quadrant. So we don't even have to think as to which quadrant are we going to use. We are going to use the first quadrant. You don't even have to draw a Cartesian plane for that. You can just draw a right-angled triangle. And then right there, you substitute the angle that is given, which is 26 degrees. In a right angle, in any triangle, in fact, the sum of angles, which is in this case 26 degrees plus 90 degrees plus that third angle, the sum of those angles must always give us 180 degrees. And if we do our maths, we will get that actually the third angle is then going to be 64 degrees. So we will then label as well that third angle to be 64 degrees. And then we have labeled the angles. We must then label now the sides of that right-angled triangle. And to do so, we must come back to our piece of information. We know that we're given cos here, and cos is the adjacent side over hypotenuse. So that means the adjacent side is 1. But the adjacent of which angle? Of 26 degrees. So here we are going to have 1 because this is the adjacent side of 26 degrees. And then the hypotenuse is going to be P, as you can see from the given information. And we have a missing side, as always, and then we have to determine that missing side now, which is the vertical side. In this case, we don't know the value of P, and we don't have to have the value of P. We just have to express that third side in terms of P. Right? And that will require us to use our Pythagoras theorem. X squared plus y squared is equal to r squared. In the place of x, we substitute by 1. In the place of y, we substitute by y. In the place of r, we substitute by p. And then we have ourselves y squared is equal to p squared minus 1. And then we take the square root on both sides, the square root, and then we have y is equal to the square root of p squared minus 1. And why do we always take the positive 1 now? Can we say plus or minus a square root of p squared minus 1? No. Why? It's because, remember, we said our right-angled triangle is in the first quadrant. And in the first quadrant, as we learned in the previous episode, y there is always positive, and x there is always positive. So for this kind of question, we don't even have to say plus or minus. We always pick the plus. But why? It is because our right-angled triangle is in the first quadrant. All right. And then let us therefore answer the required question, which is 6.1.1. Sine of 26 degrees. Opposite. Okay, let me label that. Opposite is the value of y, which is the one that we've just calculated, which is root squared, a square root of p squared minus 1 all over hypotenuse, which is p. And that, folks, is how we calculate that answer for 6.1.1. Then let us move into calculating 6.1.2. 6.1.2. Let us calculate that one, 6.1.2. So we see that now, okay, we have cos of 52 degrees. The angle that we have now is not within the right-angled triangle. Previously, we dealt with 26, which was a walk in the park, because 26 was already in that right-angled triangle. But now we don't have 26, we have 52 degrees within the question. Then how do we link now 52 degrees to one or to both of those angles within that right-angled triangle? We must link 52 degrees to one of those angles or to both of them. So it could be linked through so many things. Specifically for this, we will use a double angle, obviously, but you can consider also a reduction formulae in other questions. Consider also compound angle. Consider also the double angle. So it's not always a double angle, as you will see just now, but you can also consider a reduction formulae. Remember, that is 180 minus, 180 plus, 360 plus, and so on. You can also consider compound angles, or you can also consider a double angle. So it's not always a double angle, but in this case, it is a double angle. How do we see that? We see that actually 52 degrees can be rewritten as 2 times 26 degrees. You press in your calculator, 2 times 26 degrees, you must then get 52 degrees. So that leads us to then the double angle of cos. And what is the expression for that? It could be 1 minus 2 sine squared 26 degrees. Could be that. Or you can use 2 cos squared 26 minus 1, or cos squared 26 minus sine squared 26. It's up to you. Then we say, okay, 1 minus 2 in the place of sine 26 degrees, we will substitute what we get from the diagram. What is sine 26? Opposite, that is the square root of p squared minus 1 all over hypotenuse, which is p. And then we must then remove the brackets. How do we remove the brackets? We say, oh, okay, 2 the square will then square the numerator and then square also the denominator. Speaking specifically of the numerator, when we say 2, when we say a square root of p squared minus 1 all squared, that will give us a p squared minus 1. So that is for the numerator. And then for the denominator, when we say p to the power 2, we'll get p to the power 2. So nothing hectic. So in the denominator, in the numerator, we will be left with p squared minus 1. In the denominator, we will be left with p squared. Right. And now you will then perform your algebra to ensure that you add these two fractions properly. You must then take LCD, p squared, and then you will be left with p squared on this side minus 2p squared minus 1. And then you remove the brackets, you have your p squared minus 2p squared plus 2 all over p squared. And then p squared minus 2p squared, that would be minus p squared plus 2 all over p squared. And that would be your final answer. And folks, the last time we did trigonometry in this question was the time when we were here. We were substituting for the double angle. From this point onwards, all that we have been doing is algebra. So if you are a bit confused here, you are not struggling with trigonometry, you're struggling with algebra, adding of fractions, removing of brackets, and so on. So perhaps you can go and brush up on that specific area, which is algebra. All right, now let us focus on 6.1.3, which is tan squared 64 degrees times p plus 1. So we must know first what is tan of 64 degrees. That is the opposite of 64, which is 1, and then over the adjacent, which is the square root of p squared minus 1. So we will then substitute here in the place of 64 by 1 In the place of tan 64, we will substitute by 1 over square root of p squared minus 1. And then we say all squared times p plus 1. And then from there, we must then remove the brackets. How do we remove the brackets? We say the numerator, which is 1, and then we say that 1 to the power 2, and then we'll get 1. And then we say the denominator, which is the square root of p squared minus 1. We square all of that as we have seen in the previous exercise 6.1.2. That will therefore become p squared minus 1. So we have just removed the brackets now. All of that multiplied by p plus 1. Looking at the denominator, we have there p squared minus 1. So that is similar to a squared minus b squared. How would we factorize that? It's a difference of two squares. So it would be a minus b times a plus b. Again, folks, this is not trigonometry, it's algebra. And then how do we therefore simplify p squared minus 1? Same thing, it's a difference of two squares. It would become p minus 1 times p plus 1. So within the denominator now, we will say, okay, this is p minus 1 times p plus 1. Then we multiply all of that by p plus 1. And then, therefore, we will see that, okay, p plus 1 cancels with p plus 1, and then we are left in the numerator with 1, in the denominator with p minus 1. And that, folks, that is how it goes. Now, moving into the next slide, I think you already know what it is. Yes, an exercise under this category whereby you are given one piece of information, and that is in this case cos 52 degrees is equal to t. So you will use that to sketch a diagram, answer following questions, and so on and so on. But I wanted us to focus on 5.1.2. So I want to use that to demonstrate how would you go about answering such a question. And then when we have unpacked that, perhaps we can add here 5.1.3, whereby you will answer this question, sine 19 degrees. It's a similar method, but I will use 5.1.2 to demonstrate that method, and then use 5.1.3 to apply what you have learned in the demonstration. All right. So I'm assuming now you have attempted the question. You have your right-angled triangle, all your three angles, and then you have all your three sides. Then we will use 5.1.2 to demonstrate this specific method. And then after that, you will attempt or apply your understanding of that method in answering 5.1.3. And let us say it is for the same 4 marks. All right. So previously, I think you saw when we dealt with a double angle, we said we always link the required angle to one of the given angles or to both of them. And we use either the reduction formulae, any of the reduction formulae, and then if that fails, we can explore the compound angle, and if that fails, we can explore the double angle. Previously, we worked on, was it 52 degrees? Yeah, I think it was 52 degrees. And we said that 52 was 2 times 26 degrees in the previous exercise. And that was a double angle. It was a straightforward, it was a forward double angle method. But in this case, it's more or less of a reverse or more or less of a reverse uh, double angle method, 5.1.2. We want the value of cosine of 19 degrees. But we see here that actually this 19 degrees, how do we link it to any of those angles in the right angled triangle? We see that, okay, we now need to multiply the required angle as opposed to the given angle. We multiply the required angle to get the given angle, which is 38 degrees. And that is different from the previous example, where we had to multiply the given angle. 26 degrees was given. 52 degrees was required. And that is different. That is if when we multiply the given angle to get the required angle, that is a forward double angle approach. We saw it here in 6.1.2. We multiplied, we said, okay, 52 degrees, which is the required angle. We multiplied a given angle, which is 26 degrees. And we used this method in 6.1.2, a straightforward or a forward double angle method. But now it's different. How is it different? We are multiplying by 2 the required angle to get the given angle. We will still, yes, use the double angle, of course, which is cos 2x is equal to 2 cos squared x. Why are we using the one with 2 cos squared x minus 1? It's because the question is asking us about cos. So if we were being asked by sine, we were going to use the one that says 1 minus 2 sine squared x. In this case, x is equal to the required angle, which is equal to 19 degrees. So we must therefore substitute here and say, okay, cos 2, in the place of x, we substitute by 19 degrees. We substitute by 19 degrees and say equal to 2 cos squared x. In the place of x, we substitute by 19 degrees, and then we say minus 1. Minus 1. And then from here, we say, okay, cos 2 times 19, that will be 38 degrees, which is equal to 2 cos squared 19 degrees minus 1. And then we know what is cos 38 degrees. Why? Because we have 38 in the diagram. So what is cos 38 degrees? It would be the adjacent side, cos 38 degrees, the adjacent side, 1 minus t squared, all over the hypotenuse, which is 1. So cos 38 degrees is the square root of 1 minus t squared. So we will then substitute in the place of cos 38 degrees by a square root of 1 minus t squared. And then we say 2 cos squared 19 degrees minus 1. Then from there, we try to make cos 19 degrees the subject of this equation. Very simple. We take the negative from the right-hand side all the way to the left-hand side of the equation, and then it changes from negative to positive. And all of that will be equal to 2 cos squared 19 degrees. And then from there, we divide now by 2, a square root of 1 minus t squared plus 1. We divide all of that by 2. Why? Because we want to remove this 2. And then we say equal to cos squared of 19 degrees. And then we say, now that we have a square in cos, we must then take a square root on both sides. Take a square root, take a square root. Then we will have as the final answer a square root of the square root, 1 minus t squared plus 1, all divided by 2, and that gives us a cosine of 19 degrees. And that, folks, is how it goes. That is how it goes. Remember, there is the forward double angle approach, which is we used in the previous exercise, and there is the backward double angle approach, which is what we have demonstrated right now. So when do we use the forward? Is when you have the required angle and the given angle. But in order to get the required angle, you must multiply a given angle to get the required angle. So the required angle is the one that appears in a question, and the given angle is the one that appears in a right-angled triangle. So if you get a question whereby you must multiply a given angle or an angle in a right-angled triangle by 2 to get a required angle. That is a forward double angle approach. However, if you have a scenario whereby you have a required angle and the given angle, but in order to get now the given angle, you must multiply the required angle by 2, which is this scenario. Then you apply the reverse double angle method, which is demonstrated here. It's always going to be a double angle, of course, always. But you use this one, 2 cos squared x minus 1, when you have been asked to calculate cosine. However, if it is sine, like in 5.1.3, you will then use the one that says 1 minus 2 sine squared x minus 1. All right. And that, folks, is how it goes. Then let us go to our last two questions. This one is falling under the third category of being given one piece of information, but it is more or less of an advanced level. We are given, well, you can say two pieces of information, but it's actually one piece and another piece. They don't work in the same diagram. That is my point. The first piece of information will be used to produce one diagram. The second piece of information will be used to produce a separate diagram. So at this point, I do want to assume that you have a proper understanding of how to sketch a diagram. For example, in cos 22 degrees equal to P. That on its own will give us a diagram. And then sine 38 degrees equal to Q. That on its own will give us another diagram. So a question of how do we draw then this diagram? It's a question that we have answered in the previous exercises extensively. A question of how to draw this diagram. It's a question that we have answered in the previous exercises extensively. So I do believe that at this stage, answering a question of how to sketch, it's something that we shouldn't stress that much. So I will just draw then the diagrams without explaining how to sketch or how did we sketch those diagrams. And then if you want to verify, you can pause the video and then compare, and then attempt and then later compare your diagrams with the ones that I will draw just now. So the angle is 22 degrees, and then the third angle, using that property, sum of angles of a triangle add up to 180 degrees. Then we get that diagram. The hypotenuse is 1, the adjacent side of 22 degrees is P, then the opposite side of 22 degrees is 1 minus P squared. I do have a confidence that you are able to arrive at this stage. And then similarly for the second piece of information, we have angle 38 degrees here. And then using our property, we say that, okay, we calculate the third angle, we get 52 degrees. The opposite side will be Q. The hypotenuse will be 1. The adjacent side will be 1 minus Q squared. I do have a high confidence on your ability to sketch this diagram or these diagrams. Your understanding of how to get here, I do believe that it has been sharpened up until now. So the main focus, therefore, of this question would be to illustrate how do we then use those two diagrams to then answer these questions. Sine 68 degrees, we will search for a diagram here that contains 68 degrees, and that is the first diagram. What is the opposite side of 68? That is P. So we have P. What is the IJ? What is the hypotenuse of this triangle? Is 1. So we have P over 1. So sine 68 degrees is basically P. Right? Then cos 16 degrees? That is a lovely question, actually. A very lovely question. 16 degrees. We will now remember what I had mentioned previously. The purpose is to link these 16 degrees because when we see through these diagrams, we don't have 16, but we must then link that 16 to one of those angles or to two of those angles. Using what? It could be reduction formula. You choose any of the reduction formulae which we have covered in the previous episode, or you can explore compound angles, or you can explore double angles. It depends. In this scenario, we will explore actually the compound angle. How? We must go to these two diagrams and find angles that we can add so that we can get 16 degrees. And that would be 68 degrees minus 52 degrees. You press that on your calculator, you will get 16 degrees. What does that mean now? That means in the place of 16 degrees, we can substitute by what? By 68 degrees minus 52 degrees. And that, folks, is a compound angle, of course. What is the compound angle, of course? What is the pattern? C, C, S, S. Cos, cos, sine, sine. Cos, cos, sine, sine. C, C, S, S. And what happens to the sign now? Remember that capital letter C in cos, we can assume it to stand for change. What are we changing? The sign that was negative must become positive. That is what we are changing. And then from there, folks, we open a pair of brackets. Here we will substitute the value of cos 68 degrees as per the first diagram. What is that expression? That is the adjacent side, which is the root of 1 minus p squared over the hypotenuse, which is 1. Cos 52 degrees. 52 degrees is in which is on which triangle? The second one. Adjacent side, which is Q, over the hypotenuse, which is 1, plus sine 68 degrees. 68 degrees is in the first right angled triangle. Opposite side, which is P, over the hypotenuse. Sine 52 degrees in the second right angled triangle. Opposite side, which is root 1 minus q squared all over hypotenuse, which is 1. And then you multiply now the numerator with the numerator, we get q. The numerator with the numerator, we get q root of 1 minus p squared, plus the numerator with the numerator, we get p 1 minus q squared. Then we multiply the denominators. 1 times 1, that is 1. We don't have to write 1 as a denominator. And that, folks, is the final answer for cos of 16 degrees. Now let us go to our very, very last question. This is an interesting one. Love it. So here we are given that cos 22,5 degrees is equal to A over C. That is our very last question in episode 2. And that will be cos 22,5 degrees is given as A over C. But we are also told that A squared plus B squared is equal to C squared. So we must sketch a right-angled triangle here in the first quadrant. Why in the first quadrant? Because our given angle, which is 22,5 degrees, is in the first quadrant. And then our definition of cos is the adjacent side over the hypotenuse. So the adjacent side now seems to be A, the hypotenuse seems to be C. So we don't know now this other side, the vertical side, which is Y. However, this second piece of information, ax squared plus bx squared is equal to C, seems to be like a Pythagoras theorem, whereby we have x squared plus bx, plus cx, x squared plus y squared is equal to r squared. So in this case, it would be appropriate to say, oh, so x is equal to A, as we can see in the right-angled triangle that we have. It would be appropriate as well to say, oh, so r is equal to C, as we can see in the given right-angled triangle. Therefore, that means y is equal to B. And therefore, here we have B. All right, that is how we sketch the right-angled triangle. And then we show that, okay, 2AB all over C squared is equal to root 2 over 2. That should be a walk in the park. We say 2AB all over. We can simplify C squared to be C times C. What does that mean? That means we have 2A over C times B over C. So this C can divide A and the second C can divide B. Now, let us go to our diagram. What is A over C? That is cos of 22,5 degrees, which is adjacent side over C. And what is B over C? Now that is the opposite side over C, which is the hypotenuse. Sine 22,5 degrees, opposite side being B and C being the hypotenuse. So back to what we have here. We have actually 2 in the place of A over C, we can substitute by cos of 22,5 degrees. And in the place of B over C, we can substitute by sine 22,5 degrees. And that, folks, is the expression of the double angle of sine. 2 cos sine or 2 sine cos. It doesn't matter. The arrangement, whether we begin with cos, we end with sine, or we begin with sine and end with cos, it doesn't matter. So this is an expression of the double angle of sine. So to take it back now to the double angle, we will have sine 2 times what? 22,5 degrees. And what is that? Sine 2 times 22,5 degrees shall become sine 45 degrees, which is equal to 1 over root 2. We rationalize that. You can just say root 2 over root 2. You press your calculator. Root 2 times 1, root 2. Root 2 times root 2, 2. And voila, you have your final answer. All right. That was a lovely, lovely episode. I do trust, pray, and believe that you have enjoyed yourself.
And it's a wrap, Buffet 2. Thank you for tuning in. We hope this tutorial brought you one step closer to becoming a star. If you want more, let us match you with one of our patient and passionate facilitators who will walk you through the principles and concepts at your own pace. You can also sign up for our termly virtual revision initiative, designed to sharpen your problem-solving skills and boost your confidence for school examinations. All our contact details are in the description below. And hey, they say good people shall share, so as a good person, kindly share this with your community. Lastly, kindly like, subscribe, and comment below to let us know what you'd like us to cover next. Keep improving, keep becoming a star. The journey continues with Basics to Brilliancy, mastering the basics and mastering the art of problem solving.